Yes, sir.
Yes, sir.
Okay. So, so let me share the screen first. Just a minute. Okay.
স্যার বলছি যে একটু ডাউট ছিল আগের দিনের পড়া থেকে।
Without
বইয়ে লেখা আছে যে যেগুলো কম পাওয়ার রেটিং এর মোটর হয় সেগুলোতে ইন্টারপোল মানে নাম্বার অফ পোলস এর হাফ থাকে, এটা কেন?
কি বলেছে? কোন বইতে বলেছে?
বলেছে যে
বলো।
ভীমরাতে একটা লাইন আছে যে যে কম পাওয়ার রেটিং এর যে মোটরগুলো হয় সেই মোটরগুলোতে নাম্বার অফ ইন্টারপোল মেন পোলের হাফ হয়, মানে এটা এটা কেন, এটা বুঝতে পারিনি।
Actually, number of interpoles should be the number of neutral. Okay, geometric neutral, and the number of geometric neutral is equals to the number of poles. So in that case, the number of interpoles should be equals to the number of main poles. Okay. Now, suppose
Okay.
you have a low rating machine and you don't want to spend that much money. Okay, so then you can reduce your number of interpoles. So then also you will get some sort of advantage of interpoles, not the full advantage of interpoles, because if we use the number of poles and equals to number of interpoles, then only you will get the exact correction at the interpolar region. Otherwise, we won't. Okay, so for lower rating machine, you can save
ওকে,
your money.
আর একটা জিনিস আপনি বলেছিলেন।
Okay, continue.
হ্যালো, হ্যাঁ, আরেকটা জিনিস আপনি বলেছিলেন যে সিলভার গ্রাফাইটটা ইউজ করা হয় অ্যাজ এ ব্রাশ মেটেরিয়াল, এটা ওই লেস দেন 30 ভোল্টেজের যে মোটরগুলো আছে সেগুলোতে ওই অডিও ফ্রিকোয়েন্সি কমিউটেশনকে এফেক্ট করে, সেটা মানে রিডিউস করতে সাহায্য করে। তো অডিও ফ্রিকোয়েন্সি কি করে কমিউটেশন প্রসেসটাকে এফেক্ট করতে পারে?
না, উল্টোটা আর কি। মানে কমিউটেশনে যে তোমার মানে
সরি, রেডিও ফ্রিকোয়েন্সি।
অডিও ফ্রিকোয়েন্সি, যে মানে সরি রেডিও ফ্রিকোয়েন্সি। রেডিও মানে হচ্ছে তোমার জেনারেলি আমাদের যে তোমার রেডিও ওয়েভ যেগুলো আসে না, সেই ওয়েভ গুলোতে তোমার যে কোনো ধরনের ফ্লিকারিং বা চ্যাটারিং ডিউরিং দ্য স্পার্কিং, so that may hamper. That you also, I think you have also experienced in your daily life. Then whenever suppose you have a faulty switch, or when the tube is sparking during the glow of the tube, then also you will have some interference in the radio. So if you are listening some radio, okay, so here also the during this commutation, so if we use silver graphite, then silver graphite will help to reduce the high frequency noise which can be uh, which can be there in the radio frequency which can interfere the radio frequency. এই নয়েজটাকেও কমাতে পারে কিছুটা যদি তুমি সিলভার গ্রাফাইট দিয়ে করো। কার্বন দিলে তোমার স্পার্কিং এবং চ্যাটারিংটা বেশি হবে। সিলভার গ্রাফাইট দিলে ওই যে মানে ওই অর্ডার, এটা এক্সপেরিয়েন্স মানে প্র্যাকটিক্যালি করে দেখা গেছে যে যদি আমি সিলভার গ্রাফাইট ইউজ করি তাহলে রেডিও ফ্রিকোয়েন্সি ইন্টারফারেন্সটা কম হচ্ছে।
ওকে স্যার, থ্যাংক ইউ।
এনিথিং এলস? I think these are all YT.
স্যার আর একটা কোশ্চেন ছিল, বলছিলাম ওই
চ্যাটারিং জিনিসটা কি সেটা বুঝতে পারছি না স্যার, মানে চ্যাটারিং বললেন আপনি একটু আগে, মানে আগের দিন বলেছিলেন ওই জিনিসটা কি স্যার
Chattering is
বুঝতে
a
পারছি
kind
না।
of noise. Chattering is a kind of high frequency noise.
মানে ওই কমিউটেশনের সময় যখন ওই ঘষা লাগে তখন ওই
Hmm, hmm,
জিনিসটা
hmm,
হয় নাকি?
hmm, hmm. Correct.
ও
So
ঠিক
chattering
আছে।
is basically a high frequency noise. Okay, so so how we can understand the problem from color of sparking? So how can we understand what type of problem is there in the commutation from the color of sparking? Okay, now if the color of the sparking is whitish, okay, so we can say, so this indicates, so there are some sort of under commutation is going on. That means slightly under commutative. Okay, now if the color is yellowish or reddish, then we can say, yeah, there is some overload. So that means the current is load current. I have to write load current is high or overload. If the color is bluish, then we can say the armature terminals are short circuited. Armature terminals are short circuited. If we have some noisy spark with chattering, then we can say it's over commutative. Okay, so these are the some indication of problem inside the machine, especially in the process of commutation, and how we can say how we can uh, diagnose this problem by just watching the spark in the commutation zone or under over the commutation surface. Okay, now if we have a healthy commutator, generally the surface of the commutator is deep brown. Okay, so the color is like the wings of cockroach. Okay, so then we can say the commutator is healthy and the commutation process also going on healthy. Okay, now how we can say, next question, that how we say that the brush is located at the magnetic neutral. Okay, so how we can say that the brush which we have mount in a fixed space on the commutator surface, it is exactly at the magnetic neutral. So how we can say that? Okay, so that means there are different way by which we can say that. First one, if the operation which we having from the machine, if the operation is as a motor, then what we can do, we can shift the brush. It's not shift the brush, we can fix the brush at a particular position, and if we uh, if we flow the current in both the direction. Okay, so that means if the machine is a motor, okay, and if we flow the current in both the direction, then then we should get the same speed. So this is the indication of the brush located at exactly magnetic neutral. Okay, and if the motor is generator, sorry, if the machine is a generator, okay, and if we uh, if we flow the current in opposite direction, hmm, if we flow the, just a minute. Okay, just a minute. So we flow the current in both the direction. So that means in case of generator, the current means the field current only. Okay, we should get the same induced voltage. So these are very common method by which we can we can understand that the magnetic neutral position. The third method, which is practically is very easy, and that method is called the inductive kick method. Okay, so here we take the help of coil inductance. Though it's a DC machine, but it has some inductance. As I already told you that in armature coil also we have some inductance. In field coil also we'll have some inductance. Rather in field coil we have the inductance more than the armature coil. Okay, now suppose I have the machine like this, and the pole like this. Okay, and you have the these are the brush, and that is the rotor. Now here we have the field winding like this. This is the field terminal, and field coil is connected to this. And we have a switch. This is a kind of mechanical switch we have connected the field terminal, and the field is connected with a very low, very small DC voltage around 1.22, sorry, 1.5 to 2 volt. So only this much voltage is connected with the field coil in series with the switch. This switch is a mechanical switch. Okay, and what we have connected with the armature, that means with the brush, that is a very uh, accurate voltmeter, which is called the millivoltmeter. This can measure the voltage in the order of millivolt. Okay, so that means what we need a switch, we need a very low voltage source, DC voltage source, and we need a millivoltmeter. These three item you need to have this check. Now what you will do, we have to periodically switch on and off mechanically. Okay, and at the same time what we have to do, we have to move the brush. How we move the brush? Brushes are connected with the brush arm. Okay, so brush rocker arm is connected with the brush to hold the brush. Okay, suppose this is the brush, this is the terminal, there is a brush arm, brush holder, and this holder is connected with the brush arm. So that means when we'll move the brush rocker arm, the all the brushes are moved at a time. Okay, so that is called the brush rocker arm. Okay, so that means if there are two brushes, so that means both the brushes are connected with the same arm. So that is called the brush rocker arm. When we'll move the arm, both the brushes will move together. And if there are more than two brushes, if there are four brushes, all the four brushes are connected with the same rocker arm. Okay, so that means first we have to connect this voltage source, and we have to periodically switch on, close and open the switch. At the same time, we have to move the brush rocker arm in both the direction. Okay. Now, at the location where the millivolt will read the minimum voltage, okay, or maybe 0. So that particular location on the commutator surface is the magnetic neutral position. Is that clear? বুঝতে পারছো আমি কি বলতে চাইছি? Suppose this is the commutator, okay? So this is the commutator surface and this is the shaft. Now suppose here you have, initially here you have the brush. Now what you have to do, so one brush is here, another brush is in the opposite, suppose here, and this is the brush rocker arm. Okay, now you have to move the brush in this direction as well as you have to move the brush in this direction. Okay, so when you move the brush in this direction, this brush will move in this direction and this brush will move in that direction as well if we move in this direction. Okay, so during this movement of the brush, the point on the armature, on the commutator surface where the millivoltmeter will read the minimum is the magnetic neutral. Is that clear? So this is called the inductive kick method, because what we are doing, we are changing the current through the field coil. Okay, so though we have used a DC, but by this mechanical switch we are basically changing the current, and whenever we are changing the current, the coil which we use for the field will act as an inductance, and due to this inductance will get some sort of voltage induced in the armature. But as your brush is located in the magnetic neutral, it should ideally give 0. Okay, so the position, if it is ideally at the neutral, then it should give the induced voltage 0. But sometimes due to different problem, it may not get exactly 0. It may have some finite voltage. But ideally it should be 0 because the brush should be located at the magnetic neutral. And at the magnetic neutral, you don't have any flux. Whatever the flux you are varying in this field coil, it should not give any voltage in the armature, especially at the neutral zone. Is that
Sir,
clear?
how with that switch we can change the current in the field coil just using that particular switch?
Okay. Now, when the switch is closed, then what will happen? There will be some current.
Current will flow. So
Okay,
yes,
suppose the field is basically an RL circuit, isn't it? So this is the field resistance and this is
yes,
the field inductance. And what we are doing, we are applying a voltage source like this. Okay. So this is 1.5 to 2 volts,
okay.
which we have used. And if periodically switching on and off means what you are doing, you are applying this type of voltage. So this is your input voltage. Okay. Now this is your 0 and this is your
Okay, sir.
1.2 to 2 volt. So how it will respond? Your circuit will respond like this, like this, like this, like this. This is how it will respond. So this thing is basically the current.
Yes, sir.
Current through the field. Okay, so if there is a change in current, that means the change in flux will be there. So that means basically we are getting the transformer
Yes, sir.
EMF. Okay, so across this brush terminal, we are getting basically the transformer EMF. Because remember, if there is no relative motion, we won't get any kind of rotational EMF. DC from the DC machine, generally we get the rotational
Yes.
EMF. But there should be some sort of relative motion. Without any relative motion, we won't get any kind of rotational EMF or speed EMF. So that means in this inductive kick method, we are basically inducing a transformer EMF. But if the position from where we are tapping the voltage, if that position is exactly magnetic neutral, we should not get any voltage, ideally. Or practically we should get the minimum voltage at that point. Is that clear?
Yes, sir.
Okay. So this concludes our discussion on the construction and the different phenomena inside the machine. Then we'll start a new chapter, the characteristics of generator and characteristics of motor. So first we'll discuss the different characteristics of the DC generator. Characteristics of DC generator. So there are mainly two characteristics. One we call the no load, and the second one is the external characteristics. Mainly two: no load characteristics and external characteristics. No load means when the machine is running at no load. For generator, what kind of load we can expect? Electrical or mechanical? Any idea?
Electrical load.
So in
Electrical load.
case of generator, we can expect some electrical load. So that means if we have DC generator, so what are the classification? Did I tell you?
Separately
Self,
excited and self-excited.
self-excited and separately. Okay, separately excited and self-excited. Now under the self-excited, we have different division like series, shunt, and compound.
Series?
Shunt
Yes,
and
sir.
compound, isn't it? Series, shunt, and compound. So under this compound, we have differential and cumulative.
Immediate.
Okay, so that means these are the different uh, types of DC generator depending on their type of excitation. Okay, now I will discuss one by one. So first, I will take first no load characteristics and for shunt generator. No load characteristics for shunt generator. Okay. Now first I will show you how this characteristics we obtain experimentally. Suppose we have a generator. So this is the symbol of a DC machine. Okay. And okay, so first, before going to the shunt, let me discuss first separately excited, then you can understand better. I don't know why this board is getting hanged today. So first we'll discuss the separately excited generator. Okay, suppose we have a DC generator and these are the armature terminal and these are the field terminal. So in separately excited machine, generally we have 4 terminals, 2 for armature and 2 for field coil. Okay, and this field coil, as it is a separately excited generator, this field coil should be excited by some external voltage source. So that means some external voltage source we have to use. Okay, and we can use some rheostat in series so that I can vary the field current. And if we are varying the field current, we also have to measure the field current. So that means we need some sort of ammeter. And the reading of the ammeter will basically will give us the field current. Okay, so that means this is the external field resistance. And field has its own resistance, that is RF, small RF. Okay, and this is the voltage we applied for the separate excitation. Okay, and when we are having this field current, so that means field will give some flux, isn't it? So in this flux, the armature coils are rotating, so therefore there will be some voltage induced. Okay, and that voltage we are not connecting with any load. Okay, so that means we'll keep the armature open. Only what will connect some voltmeter. We'll connect some voltmeter with this armature. As voltmeter offers very high impedance or high resistance, so that means in this case armature is open circuited. Okay, so this no load characteristics has another name which is called the open circuit characteristics. Open circuit characteristics. Open circuit characteristics. Okay. Just a minute. Okay. So I think you have understood how it is open circuited because we have not connected anything with the armature. Only we have connected the voltmeter and voltmeter offers very high resistance. So that means basically the armature is open circuit. So this is the practical experimental setup which we use for obtaining the characteristics experimentally. Now you see, if we vary this field current and if we keep this speed constant, so that means the armature coil armature is rotating at a constant speed. Not only constant, this speed is its rated speed. Okay, so constant speed may be anything. So here I have I am taking the rated speed only. The rated speed means the speed which is written on the nameplate of the machine. Suppose 1500 rpm, 1150 rpm. Okay, so whichever is written on the nameplate, so that is called the rated speed or full load speed. Okay, the machine is rotating presently at a constant speed, and at which speed? That is the rated speed. Okay, now if we increase the field current, what will happen? The flux will increase, and if the flux increases, what will happen to the voltage, armature voltage? So the voltage will also increase, isn't it? So because you know that EA, the induced voltage, is proportional to the flux, isn't it? So that means if the field current varies, the flux will vary, and if the flux varies, the voltage will vary. So if the flux increases, voltage will increase. If the flux decreases, voltage will decrease. As simple as that. Okay. Now, this no load characteristics and open circuit characteristics is not a plot between the armature voltage and the flux. If it would a plot between these two, then what type of curve we should get? Suppose it is a plot, it is not like this, but suppose it is a plot between EA and phi, then what should be the characteristics?
Linear.
So that means it will be a linear because all the other parameters are constant. It should be a linear, but it is not the OCC. OCC means open circuit characteristics. It is not the correct OCC. Correct OCC is the plot between armature voltage. Just a minute. The plot between the armature induced voltage and field current.
Field current.
Okay, so that you should remember. OCC is not a plot between the armature current and flux. Though the equation we have, and from this equation we can say that if we plot armature voltage versus flux, then it would be a linear curve. But as it is not a curve between the armature induced voltage and flux, it is a curve between the armature voltage and field current. Then what should be the nature of the curve? Okay, now to say that what should be this nature, we should establish a relation between this armature voltage and field current. Okay, but we have this expression. Now we can say that field current determines the flux. So that means flux is somehow the function of field current. Okay, is that clear? The flux is a function of field current. Now what is this function? So that means we should know what is the characteristics between the flux and field current. Then only we can understand this function, isn't it? Are you getting? Suppose if we have the flux versus field current, we should know this nature to predict the nature of this OCC, isn't it? Because the function we don't know. If we have this relation between the flux and field current, then only we can get this function. And now what is the relation between this flux and field current? Can anybody tell me?
Hysteresis like that means at first linear.
Okay, so
And
correct. So
then it
that
will be
means if we
constant.
It will
change
get
the field
saturated
current,
after.
okay, so if we increase the field current, what will happen? The flux will increase. Because basically what is happening, if we increase the field current, the MMF, so that is NF-IF. So this is the MMF. So MMF will increase, and MMF basically generates the flux. So that means the flux will increase. Field current increases means this MMF increase, and if MMF increases, then the flux will increase. So this is how initially, if we increase the field current, we'll get a linear change or linear increase in the flux value. But after some values of field current, after a particular values of field current, the flux will not increase linearly because of the magnetic saturation, because of the exhausting number of magnetic dipoles present in the magnetic system. Okay, so that means after certain point, which is called the knee point, the flux, the flux curve will bend. Okay, so that means this function is a nonlinear function. F is a nonlinear function because initially it's a linear, but after that it becomes a nonlinear. So that means overall this function, flux versus field current, is a nonlinear function. But the nature we know. So nature is like this, like the VH curve. Okay, so that means the flux versus field current, if this nature, then what will be the nature of EA versus IF? What will be the nature of EA versus IF? As this EA has a linear relationship with phi, and phi has this nonlinear relationship with IF, so we'll get the same reflection in this curve. So that means here also the voltage will be saturated. Here also the voltage will be saturated. Okay, is that clear? বুঝতে পারছো how we are getting this saturated curve in case of EA versus IF?
Yes, sir.
Anybody has any doubt? Okay, so that means we will get the OCC or open circuit characteristics curve in this method. But the thing is, if we now decrease the field current, what will happen? If you now decrease the field current, so what will happen? So as it follows the BH curve, then if we decrease the field current, it won't return through the same path. It will follow a different path. So here also, it will follow a different path. Okay, so I have taken only the when the current is getting increased, the field current is getting increased. But if after reaching the saturation, if we now reduce the field current, the voltage will return back to a different path. Okay, and if the field current now becomes 0, still we'll get some voltage. Okay, so you just see this. Why we'll get this voltage? Due to the, so here we'll have some flux. At 0 field current also we'll have some flux. This flux is called the residual flux. isn't it? So this flux is called the residual flux. This comes from the property of the magnetic material, which is called the magnetic retentivity. Due to this magnetic retentivity, the magnetic system holds some amount of flux, which is called the residual flux. Now, if we have this residual flux, and if the armature conductor rotates in that flux, it should give you some voltage. So that voltage we are getting here. So that is called the residual voltage. Is that clear? বোঝা গেল? Okay. So this is the open circuit characteristics for separately excited DC generator. Now come to the for shunt generator. Shunt DC generator. OCC for shunt DC generator. Now, the shunt machine means the same machine. Only what we'll do, will short the armature terminals to the field terminals. So previously, what we are doing, you were connecting this to this. Now what we'll do, we'll connect this to this. So that means the armature terminal will be shorted. Sorry. So this is the A2. This is the F2. And this is the F1. So this F1 and F2 will be shorted with the A1, A2 terminal of the armature. Board is getting hacked. I don't know who is controlling my screen. Similarly, like the previous experiment, here also we'll connect some voltmeter. And the speed will be same, which is rated speed. So this is the configuration. Can you tell me why we haven't used any ammeter? Okay, so we can use some ammeter, but rheostat we haven't used here. Now when it will rotate in this field current, it should give some voltage here. Now, is it possible to have this voltage induced across the armature? Because we don't have any voltage source. So how it will generate the voltage here? That is the main doubt, main question.
Sir, by residual flux.
Okay, by residual flux, it will give some voltage.
That was, yes sir, that was present from
In the magnetic system, there is some residual
from
flux. Suppose
previous
50.
use. Yes sir.
Okay. And that will give rise some voltage of E0, as we have seen in case of separately excited machine. Okay, then what will happen? So that means the voltage will remain at E0.
Then
Okay.
no sir, that E0 will send some current in the field winding, so flux will
Okay,
again
so
increase.
that means whatever the voltage is getting induced in this will flow some field current.
Will continuously increase. Yes sir.
Okay, so this field current will give rise to some flux. Again, this flux will give rise to some armature voltage. This armature voltage again will increase the field current. Again, it will increase the voltage. So this is how, field current will generate the flux, and flux will generate the voltage. Okay, বুঝতে পারছো? তাহলে আমার শুরুতে একটুখানি ফ্লাক্স লাগছে, মানে এটা ঠিক মাছের তেলে মাছ ভাজার মতো ব্যাপার আর কি। কিছু মাছ আছে না যে মাছের থেকেই আবার তেল বেরোয়, সেখানে শুরুতে তোমায় একটুখানি তেল দিতেই হবে। তো সেটা হচ্ছে এইটা। তো যাই হোক, so we need some residual flux at the beginning, and if we have that, then the voltage will increase cumulatively. The voltage will increase cumulatively. But the question is where the voltage increase will stop. Whether the voltage increase will stop itself. Okay, so this explains that this is a indefinite process. So where it will stop?
Sir, when the flux is constant at the saturation region?
No. Actually, hard saturation বলে কিছু হয় না। ওকে, মানে স্যাচুরেশন আস্তে আস্তে চলতেই থাকে, হার্ড স্যাচুরেশন বলে কিছু হয় না। তাহলে তো আস্তে আস্তে খুব মানে একটা সময়ের পর খুব অল্প অল্প করে ভোল্টেজটাকে বাড়তে কিন্তু থাকবে, কিন্তু ইন জেনারেল ভোল্টেজ উইল স্টেবিলাইজ এট এ পার্টিকুলার ভ্যালু, আফটার দ্যাট ইট উইল নট ইনক্রিজ
স্যার
ফার্দার।
এখানে স্যার এখানে আইএফ যেটা আছে মানে ফিল্ড কারেন্ট, সেটা তো অ্যাকচুয়ালি আবার এর উপর মানে হচ্ছে আর্মেচারের অ্যাক্রস ভোল্টেজের উপরেও ডিপেন্ড করে, মানে আর্মেচার অ্যাক্রস ভোল্টেজও আইএফ এর উপর ডিপেন্ড করে, আইএফও ওটার উপর ডিপেন্ড করে। তাহলে যদি এখানে মানে দুটো কার্ভ পাওয়া উচিত, মানে দুটো যেখানে মানে একে অপরকে ক্রস করবে সেখানেই সেই জায়গা অবধি হওয়া উচিত, মানে স্টেবিলাইজ কন্ডিশনটা।
Okay, so that means what he is saying that here we are using two relations, one from which we are getting this, another from which we are getting this. Okay, so that means we have two values, one is field current, another is, for open circuit characteristics we have two values, isn't it? E versus IF. Now IF, how we are obtaining this IF? From the E0. Now what is the relation between this? E0 give you some field current. So how you are getting this field current? So this field current which will flow through this, who will determine this? That will be determined by the field resistance. So that means field current is the voltage divided by the resistance. Now you will ask me, sir, why you are not considering the armature resistance, because in this loop we have armature resistance as well, isn't it? But this armature resistance is generally very low compared to this field resistance. So therefore you have not considered that. So in this loop we will have some armature resistance, but that is very low compared to this field resistance. Okay, so therefore we won't consider that. So that means the field current is EA by RF from the very Ohm's law. Okay. Now another relation is this. So that relation we already have. So that is EA equals to ZA by A P, a function of IF into N. So N is constant. Here we are getting EA equals to, here also we have some function, and that function is linear function, isn't it? So this is a linear curve, and this is a non-linear curve. And this curve we have some name, so that is the OCC. This curve IA versus EA has some name, that is the OCC, and that is a Ohm's law curve, that is the linear curve. Okay, now let us plot these two lines. Now we have field current versus the armature voltage. So this is the line number 2 and this is the line number 1. So let me start with line number 2. As you have already obtained, okay, so this curve will be like this. Can you tell me why this line should be like this? Because this line we obtained.
রেসিডুয়াল থাকবে না
স্যার ওখানে 0 থেকে কেন স্টার্ট
একটু
হচ্ছে
রেসিডুয়াল
স্যার?
থাকা উচিত।
স্যার রেসিডুয়াল ফ্লাক্স আছে না, 0 থেকে স্টার্ট তো হবে না।
Okay, there should be some residual flux. You will have some residual flux. Now it's okay. Okay,
Yes,
so
sir.
this value you can say your phi 0 E0 value. Okay, then this E0 will give you some flux, and that flux will give you some E1. So this is your E1 value. This E1 value, actually we have some other straight line which is called this RF line, because this gradient is basically the RF. Is that clear? So this is the field resistance line. So have you understood these two lines? So this is line number 2 and this is the line number 1. Okay, so that is the straight line corresponding to the equation 1. And the curved line is corresponding to the OCC given in the equation number 2. Okay, now how this voltage is getting developed, you just see. We have started with E0 phi 0. Okay, so phi 0 is the residual flux, and if the armature conductor is rotating at a speed of nr, in this phi 0 it will develop some voltage E0. So whenever there is a voltage E0, that will try to produce some field current, and that field current is given by this, that is the IF1. Now this IF1 will add some flux with the existing residual flux and give rise to another flux, that is phi 1. And this phi 1, so that means this point is corresponding to the phi 1 and E1. Okay, so this E1 will again have some other field current, that is IF2, and this IF2 will increase the flux and it will give some voltage E2. So this is how the voltage will develop like this. It will develop like this. Is that clear? Now where the voltage, the increase will stop, that point is this point. When these two lines, which I have shown here, by line number 1 and 2, where they will intercept, is called the stable voltage point. So there the voltage will be stabilized. So this is the stable voltage point, or EA0. Is that clear? Because in the other side, they will be opposite. Okay. So that means to have a stable voltage point, we should have some intersection between these two lines. If we don't get any intersection between these two lines, then we'll not get any stable voltage point. Okay. Is that clear? To get a stable voltage point, these two lines should intersect. Okay. Now you just see, suppose the second line, or sorry, the first line is basically coming from a resistance, isn't it? Now the slope of that line number 1 is basically the resistance value. Now if I increase the resistance, then what will happen? The slope will increase, definitely. Okay, so that means if we increase the slope or increase the resistance, the slope will increase like this, then it will increase like this, then it will increase like this. So the slope will increase like this, isn't it? So that means this is a different slope, this is different, this is different. So if this is RF, suppose this is RF1, this is RF2, this is RF3. Now for this, RF3 is greater than RF2, is greater than RF, is greater than the present value of RF. So that means I am increasing the field resistance. How? By adding some, suppose I adding some rheostat in series with the field, I can increase the field current, field resistance. So if I increase the field resistance, you see what will happen for RF1, what will happen for RF2, and what will happen for RF3. Did you get my question? If we increase the field current, what will happen to this stable induced voltage EA0 if we increase the field resistance? What will happen in case of RF1?
It will get decreased if we increase the RF.
Okay, so let's suppose, let me ask somebody else. Okay, Doipayon,
Hello.
can you tell me what will happen when the value of resistance becomes RF2?
So when it becomes RF2, the IA naught will decrease, the stable point of the two graphs.
Stable point?
The intersection point of the two graphs should decrease a
The
bit.
intersection you
So
can
IA
see
naught
from
should
these
decrease a bit.
graphs that I have already drawn. So RF2 line
Yes.
and OCC line already I have drawn. You can say from this.
Yes.
So what will be the stable voltage point EA0? Will it decrease or will it increase?
Decrease, sir.
But which value will get?
So specific point.
Bolo?
So are you asking for a specific point?
I'm asking for a specific point. Just like for RF1, you are getting a specific point, isn't it? For RF1, which
Yes,
point
sir.
you are getting? You are getting this point of interception.
Oh, yes.
What about this RF2?
For RF2, it will be just touching the the
Oh,
first curve will be just touching the I2 at the step below.
I2 means there is no I2.
So the graph 2, not I2, graph 2.
Uh,
It's a graph 2, second graph, sorry.
okay. Auditro Majumdar? Auditro Majumdar
Yes,
is
sir.
there? Can you tell me
Yes, sir. Yes, sir.
what will happen
Mm,
in case of RF2?
Sir, I'm trying. It will decrease.
Ahon,
Sir, I think the point just below the green point that you have shown for curve RF1.
just below the green. Here I have not used any green point.
Just below the orange point. Sorry. Orange point. Sorry.
Just below. Now, what is the point of interception? Can you identify any point over there?
No, sir. That is a line. The same line.
Then what is the point of interception? Okay. Swastik Kanjilal,
Yes, sir.
can you tell me?
Sir, the current will the stable point will be below the RF1. I mean, the stable voltage will decrease now.
Okay. Swarnadeep,
I mean, V3 will be less than V2 will be less than V1 will be less than VF. I mean,
okay.
what were you asking?
I'm asking any specific point you'll get. So you are saying yes. You'll get a specific point and that will
No,
be
sir. For RF2 it lies on the curve 2. RF2 will not get particularly any point, I think. For RF3 it will be the voltage corresponding to IF1 for RF3.
okay. So RF3 it's okay, but what about okay. Swarnadeep,
Yes, sir. For RF2,
Hmm.
the straight line, it touches the curve 2 in its linear region
Correct. Then
completely. That means it is a tangent. It is a
tangent, correct.
tangent. So actually we are not getting a particular stabilized voltage. So the
Correct.
voltage, so this is an unstable condition, we can tell, because no particular point we
Hmm.
are obtaining. So
Okay.
this is
So that
also not
means
desirable.
okay. So when two lines are parallel or two lines are tangent, what we get from the solution? About the solution, what we can say? We'll get infinite number of solution, isn't it? Okay.
Yes, sir.
Now you have a OCC curve, which is a nonlinear curve, and you have a linear curve that is the field resistance line. So there are two curves. Curve number 1, field resistance line. Curve number 2, OCC curve. Though OCC curve is a nonlinear curve, but a major portion is linear. a major portion of this OCC is a straight line. Now, when these two straight line will overlap or become tangent, or their coefficients are proportional, so that means the solution which will get will be infinite number of solution. So that means this is from mathematics we can say. So from mathematics we can say for this RF2 which becomes tangent to the OCC curve give you infinite number of solution. Solution, what is the solution here? Solution is the voltage and current. So that means infinite number of voltage means what? What physically you will get? So you can get any voltage. So what do you mean by getting any voltage? So getting any voltage means you will get an unstable voltage. So that means voltage can vary from the all this through all this line, along all these lines, any voltage point you can get, voltage or current point. So that means your voltage will be totally unstable at this RF2. Is that clear? And this particular value of field resistance is called the critical field resistance. Is that clear? So this value is called the bolo.
স্যার বলছি যে এই পার্টিকুলার আরএফ এর ভ্যালুর জন্য তো কোনো স্টেয়ারকেস লাইক স্ট্রাকচারই তো হবে না, মানে যেমন E0 থেকে IF1 হয়, IF1 টা E1 ভোল্টেজ ইনডিউস করে, সেখান থেকে IF2 হয়,
হ্যাঁ,
এরকম তো হবেই না, তাহলে তো
হবে না।
IF1 এ গিয়েই তো থেমে যাবে, আর তো যেতেই পারবে না।
না,
তো
IF1
তাহলে
এ
কি
গিয়ে থামবে
E0
না।
তে গিয়েই
না IF1 কেন
আটকে
বলছো?
থাকবে?
তুমি যে কোনো পয়েন্টই বলতে পারো। এর ক্ষেত্রে ওর IF1 পয়েন্টটাও যা, আবার তুমি যদি এখানে কোনো পয়েন্ট নাও সেটাও ওর কাছে একই ব্যাপার। For that it don't need any increment in flux or current or voltage value. All these values will give the same. So every
কিন্তু স্যার
value. বলো?
এটা তো রেসিডুয়াল ফ্লাক্স থেকে স্টার্ট হবে, তো তো
হুম,
তারপরে কি করে ওটা ইনক্রিজ করবে যদি কোনো স্টেপ লাইক স্ট্রাকচার না থাকে? অটোমেটিক্যালি ইনক্রিজ করে দেবে কারণ কোইনসাইড করছে
হুম,
বলে
হুম, coincide করছে বলে।
সবকটা পয়েন্ট গুলো।
হ্যাঁ, সবকটা পয়েন্টই তো পেতে পারি আমি, তাই না?
আচ্ছা আচ্ছা, ঠিক, ওকে স্যার।
Okay. But if the field resistance, if the field resistance is still higher than this value, then you will get that point. Then you will get the residual voltage point. Okay, so if the field resistance is still higher than, bolo.
হ্যালো
হুম,
স্যার, আই
বলো,
হ্যাভ আ কোয়েশ্চেন।
বলো।
হ্যাঁ স্যার, বলছি এখানে যে কার্ভ 2টা যেটা আছে ওটা তো স্যার রেসিডুয়াল থেকে ওই মানে স্টার্ট হচ্ছে, আর কার্ভ 1টা যেটা আছে ওটা স্যার মানে রেজিস্ট্যান্স আরএফ এর জন্য ওটা তো অরিজিন থেকে স্টার্ট হচ্ছে, তাই না?
হুম, হ্যাঁ,
তাহলে যে স্যার দুটো কার্ভ তো কখনো একটা ওভারল্যাপ করবে না যে কোনো আরএফ এর জন্য, কারণ ওটা তো একটা অন্য পয়েন্ট থেকে স্টার্ট হচ্ছে দুটো, না?
হতে পারে।
মানে দুটো লিনিয়ার পার্ট যেটা,
হুম,
তাই তো
কেন
কখনো মানে যদি রেসিডুয়াল যদি থেকে যায় তাহলে তো কোনো ক্রিটিক্যাল ফিল্ড রেজিস্ট্যান্স পসিবল না।
বুঝলাম না। রেসিডুয়াল থাকুক না, রেসিডুয়াল থেকে
আমি
তো
বলছি
একটা
যে
সময় গিয়ে
এখানে
ওটা স্ট্রেট লাইন হচ্ছে। কার্ভটা তো এরকম।
হ্যাঁ,
The
এবার আমার কথা
initial
হচ্ছে যে
portion is again non-linear. So this portion is again non-linear. So if we start from this residual value, so this portion again will be non-linear. So you can also go by this domain theory of magnetic material. Then also you will see that initial portion of BH curve is basically a non-linear, and final is also non-linear. So
আচ্ছা, ওই জন্য
at the middle you will
overlap.
get the linear portion.
আচ্ছা,
Okay.
তাহলে ওভারল্যাপ করতে পারবে।
The
Okay,
major portion of the this OCC curve is a linear, but at the ends you can get some non-linear portion. বুঝতে পেরেছো? পুরোটা non-linear নয়, মানে পুরোটা কার্ভ নয়। BH কার্ভে কি পুরোটা কার্ভ? তা নয়। Okay, is that clear? So experimentally also we have this same experiment in our curriculum, laboratory curriculum. But I don't know whether you'll get opportunity to do this experiment in our lab or not. I'm not sure. Okay. So I think you have understood what is critical field resistance. So critical field resistance is that field resistance, that value of field resistance, where the voltage, armature voltage becomes unstable, where two lines, that means the OCC line and the field resistance line, becomes tangent to each other, and okay, and we get a unstable voltage. And if the field resistance is greater than this value of field resistance, then we get only the residual voltage. There is no voltage build up except the residual voltage. Is that clear? If the field resistance is more than this critical field resistance value, we won't get any voltage build up. We'll get only the residual voltage point. Here it is E0. For voltage build up, then this is the condition. The condition is the field resistance should be less than the critical field resistance value. Okay, so for voltage build up in a DC shunt generator, this is the condition.
স্যার এখানে যে মানে যদি ফিল্ড রেজিস্ট্যান্সটা ক্রিটিক্যাল রেজিস্ট্যান্সের থেকে বেশি হয়, মানে আপনি বললেন যে তাহলে শুধু রেসিডুয়াল ভোল্টেজটাই পাবো, মানে এটা কি সবসময় মানে অ্যাকচুয়াল রেসিডুয়াল ভোল্টেজটাই পাবো নাকি তার থেকে সামান্য বেশিও হতে পারে?
ওই সামান্য বেশি, যে মানে ওইটা বেশিটা আর কি বেশি, মানে তুমি বলছো এখানে কার্ভ যেখানে গিয়ে ইন্টারসেপ্ট করবে সোজা কথা।
হ্যাঁ, মানে ওটা খুব কম হতে পারে, মানে
ওটা খুবই
এক্স্যাক্টলি
কম,
রেসিডুয়াল ভোল্টেজ
এক্স্যাক্টলি নয়, মানে যেখানে ইন্টারসেপ্ট করবে,
মানে
হ্যাঁ, মানে ব্যাপারটা
কাছাকাছি
হচ্ছে
হতে
হ্যাঁ
পারে।
একদম এরম উঠছে, তুমি যদি খুব মাইক্রোস্কোপিক্যালি দেখো তাহলে এইটুকানি ধরো
হ্যাঁ, সেটাই
ইনক্রিমেন্ট হবে, এই ডেল্টা অ্যামাউন্ট ইনক্রিমেন্ট তুমি পাবে। এখানে ধরো রেসিডুয়াল E0 আছে, এখানে ধরো E0 প্লাস ডেল্টা ই হলো, আর মানে এই পয়েন্ট অফ ইন্টারসেপশনটা এইটা হবে, তারপরে আর ভোল্টেজটা বাড়বে না। তারপরে তার কারণ হচ্ছে এখানে যে পয়েন্টটা হয়েছিল সেই ব্যাপারটা এখানে হবে, মানে দুদিকে চলে যাচ্ছে, ওসিসিটা এদিকে চলে যাচ্ছে আর এটা চলে যাচ্ছে আরএফ লাইন, তাহলে এইটা ইন্টারসেপশন। হ্যাঁ বলো কি বলছো?
স্যার তাহলে কি এক্সপেরিমেন্টালি প্লট করার সময় আমরা ওসিসি প্লটটা E0 থেকে ডাইরেক্ট লিনিয়ার পাবো নাকি সামান্য একটু নন লিনিয়ার রিজিয়ন পেতে
নন লিনিয়ার পাবে, সামান্য নন লিনিয়ার পাবে। তো অত গ্র্যাজুয়ালি আমরা ফিল্ড কারেন্টটাকে ভ্যারি করাই না, আমরা জানি
প্র্যাকটিক্যালি প্লট করার সময়।
প্র্যাকটিক্যালি প্লট বলো কি বলছো?
তো প্র্যাকটিক্যালি প্লট করার সময় সামান্য একটু নন লিনিয়ার রিজিয়নটা পাবো,
নন লিনিয়ার রিজিয়নটা পাবে, কিন্তু যেটা হয় আমরা ফিল্ড কারেন্টটা এতটা গ্যাপে গ্যাপে ইনক্রিজ করতে বলি, মানে এই এক্সপেরিমেন্টটা করতে অনেকটা সময় লাগে, ফলে আমরা ফিল্ড কারেন্টটা জেনারেলি 0.2 অ্যাম্পিয়ারে ইনক্রিজ করতে বলি। তাহলে 0.2 অ্যাম্পিয়ারটা অনেকটা বড়, মানে এখানের পর 0.2টা নিলে তোমার এখানে কি কোনো একটা পয়েন্ট পড়লো, সেখানে তুমি ওইখানে অতটা এখানে এই ভ্যারিয়েশনটা বুঝতে পারবে না। কিন্তু আমরা যখন ড্র করতে বলি তখন বলি যে ওই জায়গাটা একটু কার্ভ করে দেখাতে, নাহলে তো হবেই না, কার্ভটা আঁকতেই পারবে না তুমি। বুঝতে পেরেছো? এবারে সেসব ছেলেরা তো ওইসব কথা শোনে না, ছেলেরা মাথার দিকে টুকে দেয়, তো জানো তোমরা তো শিখলে না কিছু। যাই হোক, নেক্সট হচ্ছে this OCC curve which I have drawn here is corresponding to a speed, and which is the rated speed of the machine. Okay, now if we change the speed of the machine, we are rotating, it's a constant speed, but if we change that constant speed at which the machine is being rotated, if we change the machine, then what will happen? Suppose if I now change the speed which is less than the rated speed. Now what will happen? Which line will change? The RF line or OCC line?
OCC line.
OCC line, because in the OCC expression we have this speed, which is nr by 60, isn't it? এইখানে এই n টা আছে, তাহলে আমি যদি if I reduce this, then what will happen? The straight line has some have some coefficient. That coefficient will reduce, isn't it? So that means what will happen? Can you tell me? কি হতে পারে যদি
For
আমি
low value of RF, we will reach the
Huh?
we will reach the
No, what about this OCC?
unstable
He has
position.
told that OCC line will change. So what will be the change in the OCC line?
The OCC will be down. It will come down.
Okay, so that means
it will be
again
lower than the
again
actual
I am
OCC.
repeating that fact that though the OCC line is a non-linear curve, but a major portion of it is a linear. Okay, but if we change the speed, then the coefficient of this linear portion will reduce. So that means the slope of this line will reduce. Okay, the slope of this line will reduce, isn't it? So that means we'll get a new OCC line which is reduced in slope like this. Okay, বুঝতে পেরেছো? So this corresponding to n1, and if we reduce further, then we should get like this. We should get like this, like this. So this is corresponding to n2, this corresponding to n3. So this slope will change, this slope now, because this slope depends on the n, depends on n, isn't it? So that slope will change. So that means what we are doing here, we are reducing the speed, keeping the field resistance same at its RF value, keeping the field resistance same at its RF value. Now I am changing the speed of the machine and we'll get a different OCC lines. Okay, so that means OCC lines are different. Now it becomes 2 prime, 2 double prime, 2 triple prime. So different OCC lines will get. Now what will happen if the OCC line becomes N2? যখন N2 টা হচ্ছে তখন কি হচ্ছে না, তখন the straight line given by this RF, it becomes again tangent to the new OCC line, 2 double prime line. You just try to observe. When the speed becomes N2, then the new OCC line becomes tangent to the existing field resistance line, that is RF line, and will get the same problem of unstable voltage, isn't it? Are you getting? So therefore this particular speed at which the new OCC line becomes tangent to the existing field resistance line is called the critical speed. Okay, and if the speed of the machine is further low, if the speed of the machine is less than the critical speed value, then we get no voltage buildup in a DC shunt generator except the residual voltage. Is that clear? So that means this is your critical speed. And if the speed is still below, that means this value, will not give any voltage buildup except this E0. Is that clear? So that means here we are getting another condition of voltage buildup. That condition is the speed of the machine, speed of the DC shunt generator should be more than the critical speed. Okay, so that is the another condition for voltage buildup. Is that clear? So here we are getting three conditions for voltage buildup. Can you list the three? Anybody? We are getting three conditions for voltage buildup. What are the three conditions? Voltage buildup means this process, this stepwise process, the cumulative process by which the voltage is getting built up in a DC shunt generator. So what are
Yes,
the
sir.
conditions?
Sir, first condition is that there should be some
Residual
residual
flux, correct.
flux.
Correct. So you can note down this point.
Second condition,
Okay. So there should be some residual flux. The magnetic system or field system you can write. So the magnetic system should have some residual flux. Okay. Number two. What is the number two? The field
the
resistance.
resistance of the field
Okay. So the
should be
field.
less than the
Correct.
critical
The field
resistance.
resistance must be less than the
Less than critical resistance.
critical resistance. Okay. And number three,
The speed of the machine should be greater than the critical speed.
the speed of the machine must be than the critical speed. So there is another condition which I am not mentioning today because already it is 3:16. So we have to end the class. So I have not asked any question that I had mentioned that in previous class that I will ask you. So today I have not asked anybody, but in the next class again I will continue this. So let me stop the share. Stop the recording.